Welcome to AI Paper Slop. We are jumping straight in today.
Yeah, no messing around. We have a really dense one today.
We do. So the paper is Next Forcing, Causal World Modeling with Multi-Chunk Prediction. It's out of Robiant, Hust, and H. Cust by Gangwei Zhu and colleagues.
And if you are building world action models, WAMs, this is an absolute must-read.
Right, so here's the TLDR for you.
Yeah.
Autoregressive WAMs right now, they suffer from just agonizingly slow training and, well, really terrible accuracy at high frame rates.
Yeah, because predicting just the next chunk of video allows the model to cheat.
Exactly. It basically just copies the previous frames. So to fix this, the researchers introduced Next Forcing. It's a multi-chunk prediction framework, or MCP, that forces the model to predict multiple future chunks simultaneously.
And the results they get are actually pretty massive.
Oh yeah, a 2.3x faster training convergence at 50 frames per second. They hit a new state-of-the-art accuracy on the RoboTwin benchmark, and as a massive bonus, you get a 2x inference speedup by using these auxiliary modules for parallel generation.
Which is huge. What's fascinating here is how this paper tackles the what they call the myopic supervision problem head on.
Right.
They're essentially taking the mechanics of multi-token prediction, which, we've seen rolling out and being so successful in large language models.
That's the NTP stuff.
Exactly. But they're adapting it for continuous video latence. It completely rewires the training dynamics of visual world models.
Okay, let's unpack this a bit, because before we look at their solution, we need to understand why the standard approach like standard teacher-forced denoising. Why is that fundamentally breaking down for high frame rate video world models?
It's a great question because the baseline approach, something like Lingbot VA, it seems like it should work perfectly fine.
You would think so, right?
Right.
I mean, you give the model a sequence of clean past video chunks, the ground truth data.
Right.
And then you just ask it to denoise the current noisy chunk. It's very step by step.
Yeah, the logic makes total sense on paper. You look at the past, you predict the immediate present. But the breakdown happens because predicting just one single chunk ahead is, well, it's a purely local task.
How so?
Well, the loss function is only evaluating the delta between the model's immediate prediction and the ground truth. Now, at low frame rates, say like 12 frames per second, there is a pretty substantial visual difference between one frame and the next.
Right, a robotic arm has visibly moved across the screen or a block has tilted.
Exactly. So the model is actually forced to learn some underlying physical dynamics just to predict that visual leap. It can't fake it.
But the industry isn't staying at 12 feet apiece. We are moving toward high-frequency control.
Right. Everyone wants to operate at 50 frames per second for, smoother, much more precise robotic manipulation.
And when you push that frame rate to 50, the visual gap between adjacent frames basically just vanishes.
Totally. I mean, frame 49 and frame 50 are essentially identical to the naked eye. So the model's optimization process, which is always looking to the easiest way out, quickly discovers an identity map.
The lazy route.
The lazy route, exactly. It realizes it doesn't need to learn complex physical dynamics to minimize its loss. It can just copy the clean context from the previous chunk, make like tiny residual pixel corrections, and pass the test.
It's like trying to learn the game of chess by only looking at one half move at a time.
Oh, that's a good way to put it.
Yeah, like you might figure out that a knight moves in an L shape.
Right.
Because you saw the piece slide across those specific squares in that split second.
Right.
But you will never, ever understand the long-term strategy of the match.
Yeah.
You aren't actually learning the game of chess. You're just tracking the pixels locally.
Yes. And building on that chess analogy, because tracking the pieces locally is so computationally cheap, this appearance shortcut basically absorbs a massive share of the gradient signal during training.
The gradient just pools there.
Exactly. The neural network optimizes for the absolute easiest path to minimize its error. So the gradients flow into the weights that just copy the previous frame, leaving virtually no pressure, none at all, on the model to update the deeper weights responsible for long-range temporal evolution.
The actual physics of the scene.
Right. This is the core of the myopic supervision problem. The model just becomes incredibly short-sighted.
I know this gets incredibly punishing computationally, too, because we're throwing massive, hugely expensive compute clusters at models that are actively avoiding learning the hard stuff.
Yeah, burning money to learn how to copy and paste.
Literally. So what does that actually look like in the training logs for these baseline models?
Oh, the performance drop-off is severe. At 50 frames per second on the random setting in the RoboTwin benchmark, the baseline Lingbot VA model hits Only a 31.9% success rate after 5,000 training steps.
Oof. 31.9%.
Yeah, it gets completely stuck on that appearance shortcut and just struggles to progress any further.
I mean, 31.9% is essentially failing. So if predicting the immediate next frame is too easy and leads to these lazy models, the logical counter move is to make the test artificially harder.
Yeah.
Exactly. We need to force the model to look further down the road.
And we've seen this general concept before in the LLM space.
We have, yeah. In language modeling, multi-token prediction has become highly influential. Instead of just predicting the next single word, you train auxiliary modules to predict, multiple future tokens simultaneously.
Right.
It improves sample efficiency, and it forces the model to build much better underlying representations of the text.
But taking that from discrete language tokens to continuous video latents, that isn't just a direct copy-paste, is it?
No, not at all.
Because language models are picking words from a fixed, discrete vocabulary. But video generation involves mapping frames into a continuous latent space, and it proceeds through iterative denoising.
Right, it's a completely different paradigm.
So how does the next forcing architecture actually bridge that gap? So the architecture uses the main heavy model to just continue its primary job, which is denoising the current chunk. But they attach 3 lightweight auxiliary modules to it.
These are the multi-chunk prediction, or MCP modules.
Right, the MCP modules. While the main heavy backbone processes the current chunk, these 3 auxiliary modules are simultaneously predicting the next one, the next 2, and the next 3 chunks into the future.
Wait, I have to jump in here. Because if the appearance shortcut is as insidious as we just established, why wouldn't these new lightweight auxiliary modules just fall into the exact same trap?
Oh, that is the million-dollar question.
Right. Because if they're lightweight, they have less capacity. Wouldn't they just absorb whatever easy gradients they can find, copy the frames, and then end up starving the main backbone of the gradient signal we desperately wanted to learn?
Yeah, the risk of gradient starvation is the defining hurdle of this whole approach. If they implemented it naively, the auxiliary modules would do exactly what you just described.
They'd just get lazy.
They would lazily copy appearances, and the heavy main model wouldn't learn a single thing about future dynamics. But the researchers bypass this by introducing what they call independent noise injection with a dedicated time step shift.
Okay, for those of us who haven't built a flow matching model from scratch recently,
Right.
What actually is a time step shift? And how does it prevent the modules from getting lazy?
Okay, so in flow matching, you are mapping a simple noise distribution to a complex data distribution over a series of time steps, right?
Yep.
The time step basically dictates the noise schedule, how corrupted the data is at any given point in the process. In the next forcing framework, the main model operates at a specific noise shift. Let's call it S main equals 5.
Okay.
But the auxiliary MCP modules are forced to operate at a much higher noise shift. Let's say SMCP equals 10.
So you are artificially blinding the auxiliary modules.
Exactly.
You are feeding them heavily corrupted data compared to what the main model gets to see.
Yes. The visual data at that higher noise level is so degraded that the auxiliary modules literally lack the local information required to solve the prediction task on their own.
Wow.
They physically cannot take the appearance shortcut because the clear pixel data they would normally copy is just completely buried under noise.
But if they can't see the pixels to copy them, how do they actually predict the next 3 chunks?
Well, they are forced to rely on the rich foundational representations being generated by the main model, because the MCT modules are dependent on the main backbone's deeper understanding of the scene's dynamics, just to decode their heavy noise. The backpropagation process routes the gradient signal deep into the main network.
That is incredibly elegant. You're basically using the auxiliary modules as a vacuum.
Oh, vacuum, yeah.
They're starving for context, so they suck the temporal gradients back into the heavy weights of the main model.
The time step shift tightens the coupling between the auxiliary modules and the main backbone. It ensures the main model does the heavy lifting of understanding the physics, while the auxiliary modules just, project that physical understanding forward in time.
Here's where it gets really interesting, though, because to ensure those gradients actually improve the foundational representations of the main model, the physical wiring of how these modules connect matters immensely.
Oh, absolutely.
You can't just bolt them onto the very end of the network and hope for the best.
No, you can't. The architecture uses what they call multi-layer feature fusion. The main backbone they use is a 30-layer WAN 2.2 transformer.
Okay, a big model.
Right. And instead of just pulling the final output from layer 30, the MCP modules pull hidden states from 4 distinct intermediate layers, specifically layers 4, 12, 20, and 30.
So it's similar to, like, a complex engine diagnostic system.
How do you mean?
Well, if you want to optimize how a car runs, you aren't just placing a single sensor on the exhaust pipe, right?
Right.
You are placing sensors directly inside the combustion cylinders, the intake manifold, and the fuel lines. That way, the feedback loop adjusts the entire combustion process from start to finish.
That's a perfect analogy. And if those sensors aren't placed inside the cylinders, you never capture the misfires happening early in the process.
Exactly.
Because early layers in a transformer typically capture coarse structural patterns, like the broad geometry of the scene. And then the deeper layers refine the fine-grained details and textures.
Okay, I see.
By fusing these multi-scale features, the temporal supervision from the MCP modules reaches into the model at various depths of abstraction.
It's also worth noting that this multi-layer fusion includes both the noisy current latent and the clean history context, right?
Yes, it does.
There's a massive amount of context flowing into these lightweight modules. So how do these 3 separate MCP modules interact with all of this data? Like, are they just operating in silos?
Not at all. They form a causal chain across depths. The flow of information is sequential.
Sequential.
Yeah. So depth 1 predicts the next chunk, right? But its output state also feeds directly into depth 2.
Oh, wow.
Then depth 2 predicts the next chunk, and its output feeds into depth 3.
So the prediction of chunk T plus 2 is explicitly conditioned on the internal representation of chunk T plus 1.
Exactly.
That inherently enforces a causal understanding of time.
It creates a temporal cascade. And to keep this computationally efficient during training, because you don't want to blow up your VRAM, all these depths share a single attention mask with the main model.
Oh, clever.
Yeah, you only compute the attention mask once per step, but you get supervision across 4 different time horizons.
See, whenever I see architectural designs like this, I immediately look for the ablation studies.
Naturally.
It's the only way to prove what component is actually doing the heavy lifting.
Yeah.
If we assume the LCP modules need to be lightweight to prevent that gradient starvation we talked about, what happens if you beef them up?
Right, like what if you give them more parameters?
Yeah, say you use 5 transformer blocks instead of just 1.
The performance actively degrades.
Really?
Yeah. The success rate drops from 86.5% when using a single transformer block down to 85.0% when using 5 blocks.
Which feels completely counterintuitive until you remember the laziness factor.
Exactly. If the module is too capable, it starts solving the problem independently. It stops relying on the main model, and that breaks that tight gradient coupling.
It stops being a vacuum.
Right.
What about the engine sensors? What happens if you remove the multi-layer fusion and just use the exhaust pipe?
Removing the multi-layer fusion drops the success rate from 85.8% down to 83.6%.
So it's a noticeable hit.
Yeah, the multi-scale gradient flow is essential for adjusting those early, coarse structural representations.
Okay, so we've mapped out the framework pretty well. We've solved the appearance shortcut by forcing multi-chunk prediction. We've tuned the noise levels with a time step shift to ensure the main model gets the gradients.
Right.
And we've wired it deeply into the backbone with causal chains. So what does this actually buy machine learning engineers in practice?
Well, the RoboTwin benchmark numbers provide a really clear picture. Next, forcing achieves 94.1% on the clean setting and 93.5% on the random setting.
Which are new state-of-the-art marks for this specific setup, right?
They are. But honestly, the metric that will matter most to engineering teams is the training convergence speed.
Oh, without a doubt. Because compute budget is the ultimate bottleneck for any AI team right now. What does the speed up actually look like?
At 50 frames per second, the baseline model requires 45,000 steps to reach its peak accuracy. The next forcing framework hits that exact same accuracy threshold in just 20,000 steps.
That is a 2.3x speed up.
It's massive.
By forcing the model to do a drastically harder task, predicting multiple futures simultaneously in a high-noise environment, it actually learns the core physics more than twice as fast. You've basically just removed the distraction of the shortcut.
Yeah, the harder objective forces the model to build an accurate internal world model faster. And the researchers demonstrated this isn't just like an artifact of robotic manipulation datasets.
What else did they test it on?
They tested the framework on the Phi World benchmark, which evaluates how well a model adheres to fundamental physical laws.
Things like elastic collisions, parabolic trajectories, gravity, that sort of thing.
Exactly.
Because I imagine tracking parabolic motion is incredibly difficult if your model only looks one frame ahead. Did it show a reduction in physical violations?
Yeah, the abnormal ratios dropped significantly, indicating much tighter adherence to actual physics. And they actually went a step further and executed a general video pre-training run on 3.5 million human activity clips.
Wow, okay. And the result?
The resulting model showed a greater than 50% reduction in fresh-it video distance, or FED.
A 50% reduction.
Yeah.
That translates to a massive improvement in the visual quality and temporal consistency of the generated video.
It's very visually noticeable, yeah.
But stepping back into the shoes of an engineer for a second, all of this added architecture raises a major red flag for deployment.
You're thinking about latency.
Yeah. If we add multiple future-predicting transformer blocks and multi-layer feature fusion into our forward pass, doesn't that just ruin our inference latency? A robotic control loop requires real-time execution. If the model takes twice as long to run, that 50 frames per second advantage is completely lost.
Yeah, and this brings us to what I think is the most practical engineering benefit of the entire paper, the free inference acceleration.
Agree? Okay, I'm listening.
The framework offers two distinct deployment modes to bypass the latency issue entirely.
Let's hear mode 1.
Mode 1 is the zero overhead mode. After the training run is complete, you literally take the MCP modules, the fusion MLP layers, the extra projection matrices, and you just discard them.
You literally just throw the auxiliary architecture in the trash.
You throw it in the trash. You strip it down to the original backbone. The main model operates with the exact same architecture, memory footprint, and baseline latency as a standard model.
But it's smarter now.
Exactly. Because it was trained under the next forcing objective, the weights inside that backbone are vastly smarter. They contain all the temporally aware representations forced upon them by the multi-chunk gradients.
So you reap all the quality gains with absolutely zero test time cost.
Zero.
That perfectly solves the latency penalty. But the paper also claims an actual inference speedup. How does mode 2 work?
Mode 2 is the parallel chunk generation mode. So instead of discarding all the auxiliary modules, you retain just the depth 1 MCP module.
Okay.
During inference, your heavy main model processes the context to predict the current chunk. Simultaneously, that lightweight depth 1 module predicts the next chunk in parallel.
Okay, this sounds exactly like speculative decoding, but applied to continuous video generation.
The mechanism is highly analogous, yeah.
Yeah.
In standard speculative decoding for LLMs, a small draft model guesses the next few tokens, and the large model verifies them, which speeds up the autoregressive bottleneck. Here, because that depth 1 module is an order of magnitude lighter than the 30-layer main backbone, appending it to the forward pass adds negligible computational overhead. Yet every single autoregressive step now advances the video sequence by 2 chunks instead of 1.
So you are doubling your stride lengths for roughly the same compute cost.
The result is a 2x inference acceleration, and the quality degradation is minimal. Running at double speed, they still maintained a 92.2% success rate on the clean setting at 50/50s.
That's incredible. So what does this all mean for the field broadly? Next forcing is a really powerful demonstration that changing what a model is asked to predict, the objective function, can be just as critical as scaling up the parameter count or expanding the context window.
Oh, absolutely.
By making the objective multi-horizon and shielding it with targeted noise, we force the model to abandon pixel matching and actually learn physics.
It effectively cures the myopic supervision problem. It takes a model that was optimizing for the next microsecond and forces it to build a robust causal chain of the future.
Which leaves us with a final, slightly provocative thought for you to chew on.
Let's hear it.
If multi-chunk prediction is this effective at forcing a continuous latent model to learn the underlying causal physics of a scene, could this type of continuous causal chain eventually replace the need for an explicit action decoding stream entirely?
Oh, that raises a really important question about the long-term trajectory of vision-language-action architectures.
Right, because right now we build systems that generate video, and then we train a separate stream to decode explicit discrete robot action tokens, like joint angles or motor torques from those frames.
Right, it's a two-step process.
But what if the physical velocity field of the predicted future is the policy? If a next forcing model perfectly predicts the continuous causal flow of a robotic arm grasping an object, mapping the exact spatial trajectory over the next 15 frames. Maybe explicit discrete action tokens are just a legacy artifact.
That's a wild thought.
Maybe we don't need to force the model to output a specific grasped token if the continuous flow of the generated video perfectly dictates the necessary movement. It really makes you wonder how long the standard step-by-step recipe of discrete actions will hold up before we just let the continuous world model drive the robot directly.